Hi everyone, thank you for having me here today. I will be discussing new display technologies from our bench, and these concepts include ideas towards remote and pixelless displays. With that, let's get started. Allow me to give a brief introduction about myself. My name is Kaan Akşit. I'm an associate professor at University College London. I obtained my bachelor, master's, and PhD degrees in electrical and electronic engineering from Istanbul Technical University in Turkey, RWTH Aachen University in Germany, and Koç University in Turkey. I took two internships at Philips Research Netherlands and Disney Research Zurich in Switzerland during my studies. I helped co-found a new research group at NVIDIA's research in the States, where I was a senior research scientist. Beyond these experiences, I am and I had collaborated with multiple institutions worldwide. Here you see a melange of their logos. With that brief introduction, we can now move on to the motivation part. Specifically, I want to talk about displays and what we want them to look like in the future. A typical attendee of this talk has access to one or multiple of these devices: a computer, a laptop, a smartphone, or a virtual reality near-eye display. In some cases, attendees in the audience are not familiar with the concept of virtual reality. Virtual reality provides a simulated experience of a similar or different world, while completely blocking the real-world image. Each of us spends a large portion of our times in front of such devices. In fact, according to a New York Post article, the average American adult spends approximately 44 years of their life staring at just screens. Research in display technologies always promises to deliver a gateway towards a meaningful contribution to other people's lives. Since we now know that displays are essential in our lives, it is natural to ask what to expect from future display technologies. Depending on who you ask, the answer may change, but let me share my predictions for the upcoming 20 years time frame. There will be multiple display types coexisting together in the future, as always, and each type will be serving a completely different purpose. A broad classification of display types goes as follows: invasive and non-invasive ones. We will have a constant contact with displays in the future. That 44 years that I was talking about will translate to our entire life at one point. Our social fabric will completely change. We will have many degrees of realism in computer graphics with the introduction of augmented reality. Both graphics and displays will also be application specific, application dependent. We just see this happening in other domains like CPUs and GPUs. They are two different type of processors. Like that, we now have displays dedicated to each application. In some cases, we will see that just streaming content from point A to point B is not the way to go. I expect to see streaming from multiple sources or semi-procedural graphics happening at some point. And the good old computer graphics were there and will always be there, as the demand in applications will never cease to exist. It may be lower than before, but there will be a demand in computer graphics in traditional sense. So you will have a relationship with the future's display at an unbelievable level. You will remember your smartphone as a relic from the ancient history. Enablers of the future's display lie in sensing and learning methods. So these wrap up my predictions for the next 20 years. With this motivation and the predictions in mind, let's get started and let's dive into asking meaningful research questions. Today I want to bring two research questions to your attention and to our focuses. The first question is as follows. How can we enable more resources to displays without being invasive, without adding more to it, without making variable displays unbearable, let's say? I believe this is a valid question to enable new experiences that require more extensive computational resources. The photograph below shows a display prototype with everything you need from the features display. But the sheer size of this optical bench is not compatible with variable. Where do we find the balance then? How do we make this variable while having all these qualities of the features display? The second question that I want to bring to your attention is how to replace digital pixels with continuous three-dimensional voxels. Voxels can be interpreted as volumetric pixels. Again, this question is valid. Obviously, in real life, we have three-dimensional information that is not pixelated, or it's pixelated at a level that you cannot resolve. On the right-hand side, you see two photographs. They show resolvable pixels on Oculus Quest 1 and 2. Both are genuinely flat images in terms of depth and far from ideal in terms of resolutions. How do we fix that? What kind of an approach would help us to fix that in the future? To address the first question, with my collaborators from University of Tokyo in Japan, we invented a new type of display called beaming displays. This work is presented at IEEE VR 2021, and it will also be presented at ACM SIGGRAPH 2021 at a special session. I will briefly talk about that in the upcoming slides. In the recent years, multiple near-eye display products are introduced in the market. Conventional near-eye displays on the market contain sophisticated parts that makes designing a near-eye display with a slim form factor a major challenge. Basically, you cannot add more to it and keep it variable. A near-eye display is a result of interdisciplinary work across computer vision, computer graphics, optics, electronics, human user interfaces, material sciences, and mechanical engineering. This is a piece of art, to be honest with you, but it's still hard to manufacture, hard to design, because all stars must be aligned to make it perfect. Though a primary effort in industry has took place in the recent year, and industry have all the experiences needed to resolve this question, heating, form factor, weight, power, and compute demand still stand as the major challenge, and will stand to be a major challenge in the 5 to 10 years time frame. So designing near-eye displays even more harder than before. Raskar and Bimper have introduced a classification of types of augmented reality devices. In the early days in their course at ACM SIGGRAPH 2006, following their classification, there are contact lens displays, as you can see from this image, near-eye displays, handheld displays, spatial displays like your computer, like your desktop display or laptop display, and projection-based displays are also there in this classification. They are all highlighted with blue boxes in this rendered image. The green color box shows our approach, which has never been tried before, and it is the first of its kind to our knowledge. Here it depicts a projector, a green box, projecting on a passive variable surface. That does not include any battery or computational resources. It is all passive, therefore fundamentally avoiding heating, form factor issues, weight, power, and computation demands. Because you can add more memory, more resources to a remote machine in your room, while you can keep your head-mounted display or near-eye display simple with our beaming display approach. So we call our new class of augmented reality near-eye display as beaming displays. Using off-the-shelf lenses, components such as lenses, conventional projectors, we build a custom projector that projects images to small screens located at some distances. In this projector, we rely on steering mechanisms to pinpoint a user's location. Additionally, we build a passive variable headset as shown in this photograph on the right-hand side. So the steered images from our projector shown on the left-hand side are projected to our all passive variable headset shown on the right-hand side. The mirror that you see on the image on the right-hand side at the top of the head-mounted display or a near-eye display, that is completely optional. If you place the projector to the ceiling, that mirror can be completely avoided, making the wearable headset composed of printed components, mirrors, and a diffusive screen. On the optical pad of our steering mirror inside the projector, we co-located a tracking camera. We let the camera track the pose of the screen and control the steering mirror so that the screen will be tracked. So let's look into some results. We report resolution characteristics for our augmented reality display, matching a conventional virtual reality near-eye display that can be found on the market. More details are available regarding the technical evaluation of the resolution in our paper. We can show full-color natural images using our prototype, and the prototype is not only dedicated to augmented reality. It can also work as a virtual reality near-eye display, as shown in this photograph. So bear with me for a second. I want to explain this in good detail. So we show a user perspective from our near-eye display, and we are trying to evaluate the tracking performance of our system. The experiment can give you an idea about the tracking and latency of our system. To understand what we're doing here, please pay attention to the virtual red circle on the left-hand side. That is placed on the same point that is intended to be placed on the same point in the visual field of view of the user. So the user is the reference. If the point is on the left-hand side, it should stick to the same position all the time. So in an ideal system, the red circle should be fixed at one location. You see a little bit of jitter in our system, but given we are just projecting images 1 or 2 meters away from the projector, I think as a first result, this is an amazing achievement because we can keep the projection fixed at a very tiny screen from 1 meter away, 2 meters away, very easily, as you can see. So we demonstrate the experience that a user would have from our system under an ideal tracking scenario. We mount our head-mounted display, near-eye display, to a robot arm, and we just simulate the motion of a person in a planned way. On the right-hand side, you see the recorded stop-motion video from the user's perspective. So this is to simulate head tilt. So what is the conclusion of our work? We introduce a new class of augmented reality display, which we call as beaming displays. This new class of display enable unlimited power because it doesn't have to be plugged to something. It doesn't require any battery to operate on the wearable headset. Therefore, enabling unlimited power and compute budget for an ERI display, while being super lightweight, as there are no batteries, no circuitry, just a piece of plastic in front of your eyes. Very simple, very basic, very lightweight. So we present our beaming display prototypes, as you have seen, and our concept solves a major problem in the display domain: wearable being overly invasive and demanding. We show that a major challenge in the designing near-eye displays can be avoided while maintaining the optical qualities. Remember, our headset is matching the current day virtual reality near-eye display optical characteristics. And display designers will greatly appreciate this outcome, I hope. As a future direction, we are considering to extend the system to multiple steering projectors. This way, a larger area can be covered. With that, we can remind ourselves the second question I raised at the beginning of this presentation. How can we replace digital pixels with continuous three-dimensional voxels? To address this question, I've been investigating holographic methods for displays, namely computer-generated holography. As this work is in review, I won't go into the full details, and I will keep it very brief. But I would like to remind that this research is a collaboration with my collaborators from the University of Tokyo in Japan and Koç University in Turkey. There are very good reasons that make me think computer-generated holography will eventually replace computer graphics at one point. As I think more about it, I can see this coming, and I think more about promises of holographic methods have to be mentioned here. Computer-generated holography promises unmatched resolutions, where diffraction limits bound conventional optical methods. In principle, holography can provide true dark levels. Furthermore, light intensities generated with holographic methods can be brighter than the original source itself. So, true dynamic range is a possibility with these displays in the future. Displays with coherent illumination, like lasers, are known to generate a larger color gamut. Holography is the only method that offers generation of instant 2D visuals at any depth, or through three-dimensional visuals, just with the same device, with the same hardware, with the same display. A dead pixel is no more a problem for a holographic display because a pixel in an image reconstructed with a holographic display is a function of all the pixels on the phase modulator or the amplitude modulator. Last but not least, learnable nature of holographic displays, like the work from Gordon Wettstein's group, Camera in the Loop, suggests that a closed-loop holographic display can offer perfection in image generation. Things like aging of OLEDs can all be avoided like in a holographic display because you can keep it always in the loop if you want, or you can recalibrate it on demand. The most significant challenge in display technologies lies in generating authentic three-dimensional visual experiences native to the human visual system. Beyond my reasons from the last slide, a common consensus in industry and academia is that a genuine holographic display is the future's three-dimensional display. Observing the publications from the recent literature reinforces my argument, as it can also be seen in this slide. But there are multiple problems in holographic displays, and I want to talk more about the coherent illuminations and their artifacts. Due to coherent illuminations, holographic displays often exhibit different transfer functions than regular optical pieces, regular optical illumination sources also, resulting in edge fringe effects, those ringing artifacts in a blurred version of an illumination. And also in that case, it's the blur is no more looking like the blur that we are used to. So the defocus blur gets weird ringing artifacts. It's often the case. So these issues in holographic displays usually degrade the visual. So it's a big problem when it comes to three-dimensional image reconstructions. In the practical sense, when things are blurred in a holographic display, things look weird due to these fringes, so the final image somewhat looks artificial and noisy due to edge fringes that one can observe. To address these fringes in computer-generated holography, we demonstrated a new CGA method that introduces a loss function and a targeting scheme, a new optimization method called dual stochastic gradient descent, a learned approach for multiple image reconstructions, and we built a proof of concept holographic display to demonstrate and to test our work. Let me first start demonstrating our technique in simulation. Here is a target image with multiple planes and highlighted regions of interest from the image. Note that this image is focused on a far plane. So in the background you see this little windmill and a floating island that is in focus. The rest of the image is out of focus. And let's observe the effect in the regions of interest that we highlighted. Classical computer-generated hologram calculation, the most commonly used methods, fail badly in multiple image reconstructions, as you can see on these two examples. Lots of noises, lots of color aberrations, and in some cases you cannot even maintain to reconstruct the same image. Whereas our method promises superior image reconstruction capabilities with respect to the classical methods in the literature. The image you see here, the regions of interest, are from our method. In this slide, you see a simulated focal stack. In practical means, we are now looking at three-dimensional scenes reconstructed using our simulation software, using our own algorithm, and we are changing the camera's focus from near to far gradually. As the focus goes through each depth level, different parts of the scene becomes sharp. In this slide, we show three actual photographs captured from our prototype, from left to right. Each photograph is captured from near, mid, and far focus planes. We switch our camera's focus to near, mid, and far and capture these photographs in practical terms. So, as the holography work is under review, I will skip having a detailed conclusion on that, and I will skip talking about the greater details of the work. I will jump to a conclusion for the entire presentation. So let's remind ourselves the two questions that we raised in the beginning of this presentation. One is, how can we enable more resources for displays without being invasive? And the second one is, how to replace digital pixels with continuous three-dimensional voxels. To address the first question, we introduced beaming display, a new way to improve display hardware and allow more computational and power budget while being lightweight and within a reasonable form factor for a wearable headset. To address the second question, we provided a new computer-generated holography method for multiplanes that improves realism in three-dimensional visuals by addressing edge fringe effects. Our method is the only method, to our knowledge, that offers fringe-free images. So the obvious next step is to merge these two novel techniques to form a unique display. a display that addresses the demands of the future. Display and graphics industry is in many ways well established, yet the future remains unsettled. Innovations leading to seamless blends of graphically created digital three-dimensional objects with the physical nature world will disturb the status quo. With that, I would like to conclude here and thank you all for listening. Now I will be more than happy to take your questions. If you need to reach out to me, you have everything you need in this slide. Thank you for listening.